Hopefully this is working now. Looks like a good chunk of people are here. It looks like the correct webcam is on, and it looks like QCam is on. So I'm coming to you guys today from my laptop, which is going to make some things a little bit challenging because my work computer shit the bed this morning. I just got off the phone with Santa Fe IT, and it looks like the network adapter in the machine died. And unfortunately, because they lock the thing down, don't let us mess with anything important on it, I can't like refresh the drivers or uninstall, reinstall drivers or anything like that. So had to get a little creative this morning, but nevertheless, we're here. I appreciate you guys being patient. So I will not waste any more of your time. Let's get into it. Please, please, please work. All right. Everybody able to see the dot cam okay? Sweet. Alrighty. Then let's do this. So of course this is MAC2312. Today is the 7th. And today we're going to begin the middle third. Begin the middle part of this course, which is all about convergence. So convergence is a word that you may or may not have heard before in other contexts. Usually when people use it in common parlance, in regular everyday speech, the word converge means to come together, right? Like I can talk about two paths in the wood diverging or converging, as in that famous poem. In mathematics, it has a slightly different meaning. So I'm going to try to introduce you to this gently. We're going to have something like 4 different notions of convergence, corresponding to different objects which may or may not converge. But broadly speaking, in math, to say something converges usually means that some infinite process leads to a finite result. And I'll be giving you several examples. And the first thing we're going to talk about today that has the ability to converge or fail to converge is a certain kind of integral. Because we've been playing so much with integrals lately, this is hopefully somewhat intuitive. And yeah, that's where we're going to begin. So let's see, I guess I need to kind of multitask between the two computers here. We can do this. Oh no, that's not going to work, is it? Shit. Okay, that's okay. We'll skip that. Unfortunately, this is a really good topic to start playing around with some software, Maple Desmos, but maybe I could do the Desmos thing. Anyway, so we've got to improvise. That's okay. So the section we're going to begin today is 7.8, and we're talking about improper integrals. You may have seen these. Oftentimes when you see a movie and they want to show you some scary mathematics, you'll see one of these symbols just drifting across the screen in some kind of slightly translucent font. An improper integral is one which measures the area of a region which is either infinite in length or infinite in height. Right? So we know that integrals can be interpreted as measuring areas. We've of course seen plenty of that. An improper integral is one where the area is the area of some region, and that region is either infinitely long, goes on and on and on forever to the left or to the right, or maybe both, or infinitely tall, i.e. you're integrating over a vertical asymptote. And it's possible to combine those two into a single thing, but we'll take it slowly, one thing at a time. If the region is infinite in length, we call this a type 1 improper integral. And if the region is infinite in height, we call this a type 2 improper integral. And there are some kind of technical challenges behind these things that I don't want to 100% brush under the rug. So, you know, when in the calc sequence, when we cover section, for example, 2.4, chapter 2 on limits back in calc 1, you probably skipped over section 2.4, which is the rigorous definition of a limit, deltas and epsilons and all that. But here we kind of need to address the elephant in the room, because the whole notion of convergence is intimately related to the rigorous definition of the integral. So I'm going to do my best to make it accessible. I'll ask that you do your best to follow along with me. So type 1 integrals generally look like the integral from some number out to infinity. Or it could be from negative infinity up to some number. Or it could be from negative infinity to infinity of, you know, some function f of x dx. So like this, or like this. And you can see the problem. Of course, it's that infinity symbol, right? So maybe I have some function, and I want to start measuring the area here. And I want to know what's the area of all the stuff out and out and out forever. All right, this should be the integral from a to infinity of f of x dx. The main problem here is coming from Riemann sums. delta x, which is always b minus a over n, can't be defined because b in this case is plus infinity. So as we went through chapters 6 and 7, every time we learned a new technique, what we really should have done to verify that that technique is kosher, and what we would have done if this was a real analysis class instead of like a basic calculus class, is go back to Riemann sums, because Riemann sums are the definition of our integrals, and verify that the Riemann sums obey whatever thing we were trying to show is true for the integrals. So for example, when we learned integration by parts, if we wanted to prove that integration by parts is kosher rigorously, we would have had to work directly with Riemann sums and show that the Riemann sum for the integral of u dv really does come out to the Riemann sum for uv minus the integral of v du. Well, here, if you're dealing with a type 1 improper integral, because delta x is infinite, the very first step in forming a Riemann sum is impossible. The first step in forming a Riemann sum is take your interval, a to b, and chop it up into finitely many, finite length subintervals. You can't do that here because the interval a to b is the interval a to infinity. And there's no way to chop that interval up into finitely many, finite length subintervals. Think about it. If they're finite in length, then you'll need infinitely many of them to cover that whole interval, because that interval is infinite in length. Or if you force yourself to cover the interval and force yourself to have finitely many, then at least one of those subintervals itself must be infinite in length for the same reason. So the main problem here is that we can't get started using any of our tricks like integration by parts, U sub, trig sub, PFD, all that shit falls down because this is not a normal integral. In other words, it's not a Riemann integral. There are sneaky ways to get around this. For example, it's called Lebesgue integration. I'm comfortable sharing this with you because it's no longer true, but one of my passwords used to be, in 1901, Henri Lebesgue changed how we integrate. Henri Lebesgue was a man who said, instead of forming Riemann sums with vertical rectangles, what if we used horizontal rectangles? And believe it or not, that gets you around this whole problem in one very, very simple, clever step, but it requires something called measure theory. And that takes several years of hard work to develop, of course. So that's not going to be our attack. Our attack instead is going to be to view this improper integral as a limit of normal proper Riemann integrals. So this is the first object we're going to discuss convergence regarding, and you can see how this kind of broad notion of convergence might connect to something like this. Integrating over this infinite interval of inputs is an infinite process. And if the result here, if the integral at the end, following whatever procedure we outline, turns out to be finite, then we would say that this integral converges. I'll be a lot more particular about that in just a minute. So let me draw that picture again a little bit larger and see if we can't kind of guess our way to a mechanism that will allow us to form a Riemann sum and thus use all the tricks that we want to use on our integrals. Okay, so here's my function f of x. Here's the number a. And I want a reasonable way to define the integral from a to infinity of f of x dx. And we know, okay, the integral from a to b of f of x dx should be the area underneath the curve from a to b. Except here, b is infinity. So this should be the area underneath the curve starting at a going all the way out forever and ever and ever, amen. But again, the challenge there is that if I try to think of that as a single integral in a single step, I can't form a Riemann sum. So all of the tricks that I would normally use aren't kosher, because all of those tricks rely on the fact that my integrals are Riemann integrals. So here's the move. Instead of trying to do the whole integral at once, I pick my favorite real number r, and I like to use capital R for this. And I look at the integral from a to r instead. The integral from a to r is a normal Riemann integral, because here the interval from a to r is finite in length. So I can do all the things I want to do there. I can form my delta x, I can form my Riemann sums, and thus I can use integration by parts or whatever the fuck I wanted to use. So here's the trick. You define the integral from a to infinity to be the limit as capital R goes to infinity of the integral from a to capital R of f of x dx. This is a normal Riemann integral. And I think you would agree that as R wanders its way off to infinity, we will get the thing we wanted, which is the area underneath f of x everywhere to the right of a. Even symbolically, if you plug in the infinity symbol here for r, this looks like that. That's pretty appealing. It turns out to work just fine. I want to take a second here and make sure we're comfy with the basic idea. So instead of integrating all the way out to infinity, I integrate out to r, find a formula for that integral, then send r to infinity. I will say that the integral from a to infinity of f of x dx converges if the limit as capital R to infinity integral a to capital R of f of x dx exists and is finite. If that limit does not exist, or is not finite, I say that the integral a to infinity f of x dx diverges. This is the lingo, right? This is the vocabulary. And in this middle part of the class, one of the things you're going to have to adjust to is that things become a lot less about calculation and a lot more about proof. These integrals are a great introduction to the concepts because you can use all of your calculation skills that you've learned over the last few weeks with regard to integration. But here I care much more about whether or not the thing converges. That's what I really care about. So let's work some examples. First, are there any questions about this definition? Okay. So for our first example here, let's say I want to calculate, if possible, the integral from 1 to infinity of 1 over x squared dx. I'm going to draw the picture here. And your graphing skills are going to be useful in this section. 1 over x squared is a graph we should know. It's an even function. It looks like this. 1 is like here. So the area I'm trying to find is all of this area going on and on and on forever here. And the way we do that is by integrating up to some number r. I find the integral from 1 to r, and then I send r to infinity, following this. So the integral from 1 to infinity of 1 over x squared dx is equal to the limit as capital R goes to infinity, integral 1 to capital R, 1 over x squared dx. As you work these problems, you may be tempted to get sloppy about writing your limit here. Please don't get sloppy about this. This is really important. Again, it might seem like a technical thing, but this integral is improper. It's not a Riemann integral. Your fundamental theorem of calculus, U sub, trig sub, all the stuff you've learned cannot be applied to this integral because it's not a Riemann integral. All of those things only work for Riemann integrals. So this very first step of expressing the improper integral as a limit of Riemann integrals is really important. And if you omit that step, I have to take off points. I don't want to do that, but it's a necessary thing for technical reasons that can't be avoided. If you want to talk about the details of it beyond what we've discussed here, I would be happy to do so. But that would have to be outside of class. Now that I do have this expressed as a limit of Riemann integrals, I can use my fundamental theorem of calculus here, which means I can use my power rule, I can use trig sub, I can use all the things that I like to use. In other words, this integral is a good old-fashioned regular Riemann integral. So I can rewrite 1 over x squared as x to the negative 2 and apply the power rule. Altogether, then I have the limit as r goes to infinity, integral 1 to r, x to the negative 2 dx. And an antiderivative for x to the negative 2 is negative x to the negative 1, or negative 1 over x. So I end up with the limit as r goes to infinity of negative 1 over x evaluated from 1 to capital R. If I plug in my bounds here, I get negative 1 over r minus negative 1 over 1, which is 1. And now, and only now, that I have this expression rather than the integral, I can take that limit. So as r goes to infinity, what does 1 over r do? Goes to 0. So I get 0 minus negative 1, or 1. All right. So does this integral, the integral from 1 to infinity of 1 over x squared, converge or diverge? I call this a convergent integral or a divergent integral.
Converge.
Yeah, this is a convergent integral. This integral converges. So you might want to get used to the parts of speech for the words. That's one of the things that people get a little bit stuck up behind. The word converge is a verb. It's something that the integral does. And the adjective form of that word is convergent. So I would say that this is a convergent integral. Let's say hence the integral from 1 to r of 1 over x squared dx converges. Or if you want to use the adjective form, we would say is convergent. And I can say more. It has value 1. So there's two questions built into every one of these problems. Does the integral converge or diverge? And also, if the integral converges, what's the value? Any questions on this example? This is a type 1 integral because the region that I'm trying to integrate over from 1 to infinity here is a region of infinite length. Yeah, so this is a type 1 improper integral. I will show you some type 2 examples, but I want to spend a little bit more time on type 1s first. And it turns out that for some reasons that'll become clear when we get into the section on infinite series, type 1 integrals are a little bit more important. Type 2 integrals are neat as well, don't get me wrong, but type 1 integrals are a little bit more important. Good question. Other questions on this? Okay, let's look at another example. Let's evaluate, if possible, the integral from 0 to infinity of x over 1 plus x squared. This is another type 1 improper integral because the interval over which I'm integrating is infinitely long. In short, if you see an infinity as the upper bound or a negative infinity as the lower bound, you can immediately conclude that the integral is type 1. So remember, a type 1 integral is one where the region is infinitely long. So as in the previous example, I'm going to begin by writing this as a limit r to infinity, integral 0 to r, x over 1 plus x squared dx. And only once I've done that can I start applying any of my integration methods. What method would be useful here? Good, this is a u-sub problem. And so just as we would in a regular u-sub problem, we make our substitution, we change our bounds. Make the substitution z equals 1 plus x squared. dz then is 2x dx. So I've got an x dx upstairs, so 1/2 will pop out. I also need to change my bounds. My old bounds were x equals 0 and x equals r. When x is 0, z is equal to 1, because z is 1 plus x squared. When x is equal to r, z is 1 plus r squared. So that's what the substitution looks like. And when I apply that, I'll get the limit as r goes to infinity, still here. Always got to write these limits. Integral from 1 to 1 plus r squared of 1 over z times 1/2 dz. And the 1/2 can pop out just like it normally does. In fact, it can come out all the way past the limit. So I'll get 1/2 limit r to infinity, integral 1 to 1 plus r squared 1 over z dz. And of course, an antiderivative for 1 over z is the natural log of z, the natural log of the absolute value of z. So this is 1/2 lim r to infinity ln absolute value z evaluated from 1 to 1 plus r squared, which is 1/2 limit r to infinity ln of absolute 1 plus r squared minus ln absolute 1. Let's start here. What is this piece? The natural log of the absolute value of 1 is, 0, right? The absolute value of 1 is 1. The natural log of 1 is 0, because e to the 0 is 1. More interesting is the other piece. Now 1 plus r squared is a positive function, so I can ditch the absolute values. What does 1 plus r squared do as r goes to infinity? It does, right? Think about the graph of 1 plus x squared. It looks like your regular parabola, so as you wander off to one side, it does go all the way up to infinity. And what does the natural log do as his insides go to infinity? Let's see. Let's see. I'm just going to show natural log in general here. It might look like he has a horizontal asymptote, but if you keep running off to the right further and further and further, the natural log function does just keep getting bigger and bigger and bigger. It just does it very, very, very slowly. In other words, let's come back here. Here's the notation I would prefer for this. This is 1/2 natural log of infinity. And the natural log of infinity is infinity. And 1/2 times infinity is infinity. So I know again that sometimes coming into Calc 2, we don't have a very firm grasp of the natural log function. This needs to change. We must develop a firm grasp of the natural log function, and firmly grasp it. The natural log function grows as slowly as something could possibly grow and still go to infinity, as its inside goes to infinity, but it does go to infinity. It just goes there very, very, very slowly. So as r goes to infinity, the inside of the log here, 1 plus r squared, that's 1 plus infinity squared, that's infinity. And then the natural log of infinity is also infinity. So I would say that this integral the integral from 0 to infinity x over 1 plus x squared dx diverges. Or again, if you want to use the adjective form here, I would say, or is a divergent integral. Okay. How do we feel about these? Do you feel like we have a pretty good intuitive grasp of type 1 improper integrals? Are there any questions we would like to ask having seen these two examples? Oh, that's just awful. Yeah, that's not yesterday's coffee. That's from at least 2 days ago. So we can use our tricks. We can use u sub, integration by parts, all the things we want to on these, as long as we first write them as a limit of a proper integral, i.e. a Riemann integral. In case you don't remember, you might want to go back and look all the way into section, I think it was 5.5 in the textbook, something like that. No, 5.1, sorry, where you first learn the definition of a definite integral. And you'll notice that they said if the function f of x is continuous on the closed bounded interval a to b, then blah, 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 blah. And it's from there that you developed your fundamental theorem of calculus. So really what we're doing with these improper integrals is breaking those rules one at a time. Here, the function f of x is continuous. X over x squared plus 1 is continuous everywhere. But the interval is not closed and bounded. It's neither closed nor bounded. Right? The interval 0 to infinity is an unbounded interval. It goes on forever. And it's not a closed set. So breaking the closed boundedness of the interval is what leads to type 1 integrals. The other way you can get in trouble is by breaking the continuity of the function. If f of x is not a piecewise continuous function, then you can run into problems as well. And those are type 2 integrals, right? In other words, if the function f of x has a vertical asymptote, it blows up to infinity somewhere. So if there are not questions on this, if we're feeling like we have a reasonable grasp of type 1 integrals, then I would like to show you a type 2 integral. Last call for questions or comments on this example or either of these type 1 integrals we've seen. Okay, then let's look at a type 2 example. I haven't yet shown you the formal way to set up a type 2 integral. I've only shown you the formal way to set up a type 1 integral. So I'm going to use this example to introduce the formal process for a type 2 integral, because it's similar enough that I think you'll be able to follow. But before that, I'm going to draw the picture. And I'm going to draw this picture nice and big. Okay, here's the graph of 1 over the square root of x. It has the point 1, 1 on it. Right here. And this time what I want is not the integral from 1 to infinity, it's the integral from 0 to 1. And that presents a whole different kind of issue, because this function has a vertical asymptote at 0. So the area I'm asking for here is all the area between 0 and 1, and that includes all the stuff up here. Do you see the problem? This region is infinitely tall. So its area might not be finite. Right? You take something that's infinitely long. What we've just discovered through these last two examples is that the area could be finite or it could be infinite. It's definitely possible to have something that's infinitely long but has finite area. I remember that blowing my mind all to pieces when I first learned it. It really shocked me. Here what we have is a region that's infinitely tall. So again, it's possible that the area is not finite. Instead of taking a limit as capital R goes to infinity here, I'm going to take a limit as capital R goes to somewhere else. The problem in this case is not coming from the upper bound, it's coming from the lower bound. It's coming from the fact that at x equals 0, this function's output is infinite, or the limit as x goes to 0 from the right of f of x is plus infinity. So what we do is this. Instead of integrating from 0 to 1, we integrate from r to 1 to find this area. And then I send r to 0 from the right. So here I would say that the integral from 0 to 1, 1 over the square root of x dx is equal to the limit as r goes to 0 from the right. That's with the little plus there, remember, of the integral r to 1, 1 over the square root of x dx. And this has the same overall effect as sending r to infinity in the previous two examples. It lets me work with a well-behaved integral. It lets me work with an integral over a region that the function doesn't have any sort of problems. In other words, the dark shaded area here is clearly finite. So I'm able to get the whole integral as a limit of obviously finite integrals. I send r to 0 from the right because in this picture, it's this lower bound that I want to move over towards here to get this whole region. I don't care about what happens as r goes to 0 from the left. That has nothing to do with my integral. So the fact that the limit is one-sided here is important, and you need to pay attention to that. So this will be the limit as r goes to 0 plus integral r to 1. And 1 over root x is x to the negative 1/2 power. So again, I'll be able to get away with my power rule here. An antiderivative for x to the negative 1/2 is 2 times x to the positive 1/2, or 2 square roots of x. So this is limit r goes to 0 from the right. I'll write it like this, why not? It's x to the 1/2 divided by 1/2 evaluated from r to 1, which could otherwise be written as 2 times the limit r to 0 plus times or of the square root of x evaluated from r to 1. So that's 2 lim r to 0 plus square root of 1 minus the square root of r. The square root of 1 is 1. And as r goes to 0 from the right, the square root of r goes to 0. So this is 2 times 1, which is 2. So this type 2 integral is convergent, or this type 2 integral converges. Therefore, so to give a full characterization of type 2 integrals, it's a little bit trickier than type 1 integrals, but I'm going to do my best for you on the next page. I just thought that this example was a more eye-opening way to do that, to at least introduce the concepts here. Do we understand why the limit is the way it is? The limit as r goes to 0 plus? It's important that we're able to wrap our heads all the way around that. Okay, any questions about this particular example? Any one of these steps, or why we're writing things the way we are? Can you imagine this R value slowly shifting to the left, allowing this region to go up and up and up and up and up? Okay, so we gave a characterization of type 1 integrals. Here's the deal with type 2 integrals. I'll recap here. To evaluate a type 1 integral, like integral a to infinity f of x dx, you need to write it as the limit as r goes to infinity, integral a to r f of x dx, and then apply whatever tricks you have for that, for the integral. And then at the end, take the limit. If you have the integral from negative infinity to a of f of x dx, you do the same thing, you just send r to negative infinity. So this would be limit r to negative infinity, integral r to a f of x dx. So type 1 integrals will always look something like this, either from some number to infinity or from negative infinity to some number. If you're unlucky, it'll go from negative infinity to positive infinity, and I'll show you how to deal with those next time. For a type 2 integral, you need to be more careful. This is one where f of x has an infinite discontinuity at a, and it'll look like integral a to b f of x dx. So the first thing to note is that type 2 integrals aren't even always obviously improper, right? There isn't necessarily anything in the symbols that are used for a type 2 integral that will make it jump out as improper. But if your function has an infinite discontinuity, i.e. a vertical asymptote at a, if that is the lower bound, then you'll write limit r goes to a from the right of integral r to b f of x dx, or if it's looking like, say, c to a, so again, the infinite discontinuity is now at the top, then this would be limit r goes to a from the left, integral c to a, c to r, f of x dx. Okay. So I'd like to do one more type 2 example, and then I'll let you guys go. Next time on Friday, I'm going to show you what happens when you have more than one of these things going on. In fact, it's possible to have all four going on at once. Remember, type 1, these are infinite length. Type 2, these are infinite height. That's the easiest way to remember which one is which. So let me look. The integral from -2 to 0, 1 over x to the 1/3 dx, something like this. Again, notice that if you just wrote this down, if I handed this to you last week, probably nobody would recognize that there's something wrong, because there's no infinities here or here. It just looks like a regular definite integral, but it's not. Why is this not a regular definite integral? Somebody help me out. Show me that you've been paying attention. Good. Not just any discontinuity, but an infinite discontinuity. It has a vertical asymptote, right? Like it's not a jump, it's not a hole. it's a vertical asymptote. It's an infinite discontinuity at 0. So the problem here is at the upper bound, not at the lower bound. And it's probably going to be helpful to look at the graph anytime you're dealing with one of these improper integrals, especially a type 2 integral. I strongly recommend sketching the graph. The graph of x to the 1/3 looks like this. He has a vertical asymptote at 0. Looks actually a lot like the graph of 1 over x. And I want to integrate from -2 up to 0. That means I'm trying to find all of this area. And that region, of course, is infinite in length. It goes forever and ever down like this. So rather than integrating from -2 straight up to 0, I'm going to integrate up to my favorite real number, r. And then I'm going to evaluate the integral from -2 to r, giving me a formula for the area that's like this. And then I'm going to take the limit in that formula as r approaches 0, this time from the left. So this is the limit as r goes to 0 minus integral -2 to r, and that is x to the -1/3 dx. That's lim r to 0 minus integral -2 to r. Sorry, no more integral now. We're going to go ahead with our antiderivative step. -1/3 plus 1 is +2/3. So this is going to be 3/2 x to the 2/3 evaluated from -2 to r, which is lim r goes to 0 minus 3/2 times r to the 2/3 minus 3/2 times -2 to the 2/3. And as r goes to 0 from the left, r to the 2/3, this is graph of f of x. Down here, maybe I'll draw the graph of r to the 2/3. Useful to remember what that on its own looks like. That looks like this. So as r goes to 0 from the left, this guy is going to 0. So this is 3/2 times 0 minus 3/2 times -2 to the 2/3. And I'm not aware of a nice way to write that number. It's just -3/2 times 2 to the 2/3. -2 to the 2/3 is the same as +2 to the 2/3 because of the 2 in the power. All right. That's like -2 squared, and then you take the cube root. Now, we could clean this up a little bit, I suppose. I could write this as -3 times 2 squared to the 1/3 over 2. Not much more you can do there. I can't let these guys interact because of the 1/3 power here that takes precedence. So that's -3 times the cube root of 4 over 2. Yeah, this is the game. So that's how you handle type 2 integrals. You have to identify where the vertical asymptote is, and then sneak up on it from whichever side is appropriate given your integral. Is the vertical asymptote at the left or lower bound, or is it at the right or upper bound? And then the type 1 integrals are a little bit more intuitive. You just send r to plus infinity or to minus infinity. This is where I'm going to stop for today. Next time I'm going to show you what to do when you mix these things, like how do you do the integral from negative infinity to infinity of 1 over x? Because that's got all sorts of problems, right? That's got a problem at negative infinity, a problem at 0 from both sides, and a problem at positive infinity. So you can mix type 1 and type 2 integrals into a single thing, and I'll show you how to handle those. And then the more exciting thing is we're going to start developing some theorems. We're going to start developing some rules that will help us tell when these integrals converge or diverge without evaluating them. And that's going to be the big important step for us. So we're entering into the part of this course that scares people, right? The part of this course that scares people is undeniably the convergent stuff, improper integrals, sequences, and series. This is the hard part of Calc 2. If you have been having trouble budgeting your time to study for this class, I want to strongly recommend you take a moment to sit back and re-evaluate your lifestyle at the moment, because you are going to need to dump a lot of time into the next few weeks. Exam 2 is usually the lowest scoring and hardest exam in this class. I'll tell you that exam 3 is usually gentler. People usually have an easier time with exam 3 than exam 2. So if you can get through this, you'll probably be okay. But you need to work very, very hard to make sure you get through this next section. It's not easy. After we finish section 7.8, we're going to jump to section 11.1 in the textbook, which is on sequences. So if you're not finding this improper integral stuff terribly challenging, I want to encourage you to start reading ahead on sequences. But that is it. All right, that's where I'm going to leave you guys for today. I am working on your exams. I'll get them done as soon as I can. My rule is always 1 week, so I'll have them for you no later than next Monday. And that's it. I'll see y'all on Friday. Okay, take care.